Welcome to the last lecture. Today I will talk about a bit different thing. So today I will not talk about black holes, but still some about AdS quantum gravity. So I want to talk about today role of AdS orbital singularities within this AdS5 example we have been discussed so far. So yeah, holography on AdS singularities. This is that has not been appeared yet, but I hope it will be appeared at least within this year. So our question is simple. So what happens to the spectrum of quantum gravity on AdS if we put orbital singularities? So in yesterday and also in the first lecture, we saw that there are many interesting degrees of freedom in quantum gravity, black holes, gravitons, and so on. And I want to put another additional interesting degrees of freedom by putting orbital singularity on the space-time. And actually, these answer to this kind of question is quite well known, that as there will be some massless degrees of freedom from brains wrapping these singularities. One of the most famous example is the tensionless string of 62G series from 2B string theory on singularities, probing singularities C2 mod gamma. Today, we will revisit this problem in the context of a simple AdS5 example we have been discussed so far. So we want to study for the n-equals 4 spin-mills on S3 bounded by gamma, which will be dual to 2B string theory on AdS5 mod gamma times S5.
So yeah, the RP4 is on the S3, not the S5.
Yeah. So in the dual picture, the orbital fixed point will be at the center of waiting string. In today's talk, gamma is a finite subgroup of SU2 of AD type, written as this. So for the A type, this is nothing but the cyclic group Zn, and for D and E type, we have dihedral group, tetrahedral group, octahedral group, and so on. And actually, this kind of setting was first, as far as I know, considered from this paper after the Modasena's paper, and also later revisited by this paper. And even in that paper, people said that there should be lots of light degrees of freedom in on the quantum gravity in this AdS modeled by orbitals. But today I will quantitatively analyze this problem, focusing on the low-lying spectrum, and I will show you that there exists some non-trivial vacuum structure and the implication of S-duality and one-form symmetry. So we'll again consider n-equals 4 spin-mills, but for the moment we will we will not consider just UN group. We'll just consider arbitrary gauge group G on S3 mode gamma times S1, where gamma is again the finite subgroup of S2. And this gamma will act on S3 as the whole fiber circle of S1, whole fiber circle S1 of S3. And introducing this orbital will break half of supersymmetries of n-equals 4 spin-mills.
When you say S3 pushing gamma across S1, that S1 I should think of as the time direction from that side, or what is that?
This the time circle.
Time circle.
Yeah.
Thank you.
Sorry, when you say gamma acts on half fiber circle, I understand that if gamma is a subgroup of U1, only Zn.
No. Actually, yeah. Well, Zn case this is true, but yeah. So I abused some notation, but yeah, this is the precise definition. So let me be more concrete by defining the index. So basically, we want to define the index on this orbital sphere. This is nothing but the index I introduced earlier in 2 talks. And the orbital gamma will act on the following. So we have SO4 rotation symmetry on S3, and which is nothing but SU2 times SU2, and gamma is nothing but the finite subgroup of some SU.
Okay.
And this index will count BPS states which are invariant under the action of gamma. But one interesting thing here is that one can also turn on the discrete gauge holonomy around the Hopf fiber circle gamma.
Sorry, this just I want to understand the action here. So this action is free on S3 or has fixed points?
Free.
So this is the standard C2 mod AD bed quotients that people consider, right? Because in singularities.
You mean bulk?
In the bulk, yeah.
Yeah.
So that produces like lens spaces and things like that.
Yeah. So when ZK, this is nothing but the lens spaces.
So can you explain why it takes half of this matrix? Is there easy to understand that?
So yeah, I didn't write down the supercharges here, but if you see the supercharges, you can find that there are only half of supercharges are invariant under the gamma action, meaning that it should not charge it under this group.
You can correct me, but at least if you think of C2 mod gamma, you think of that as two complex coordinates, then you have to phase the two complex coordinates in the opposite place. And so that's one additional condition.
Yeah.
Right.
Basically, by examining spin of supercharges, you can read out what kind of supercharges are reserved and what kind of supercharges are flow. So yes, so today we're gonna study in this setting, and
Maybe you can back up for a moment and share.
So
you're modding out by some subgroup of the rotation.
yeah, SE2, AD type.
SE2 sits inside SF, that's SE2 times SE2 is one of the two, the diagonal one.
Yeah, there's a full rotation symmetry on S3. Yeah.
One of the two. And the supercharge will be charged under the other S2. It's the one that will be preserved.
SE2, yeah.
Will be charged under the other S2.
If it were diagonal, it would not have been free. It would have fixed points. This is the free action.
Yeah, correct.
Singularity rules in the bulk.
Yeah, it is free on S3, and singularity fixed point will be on the center of AdS. So yeah, for to have some better intuition, let me give you some easy example. Let us consider the U1 case with, and also the orbifold action is nothing but the ZK. Then orbifold now acts on the Hopf fiber circle by a rotation of 2 pi over k, and naively states with J2 equals 0, mod k can only contribute to the index, right? They are the invariant states under the action of gamma, action of ZK.
What is gamma?
Gamma, Hopf fiber circle, Hopf fiber circle, that's one. But then, since we are now working on the gauge series, meaning that you can turn on some discrete gauge holonomy along the Hopf fiber circle and consider the charge states which transform by a non-trivial phase into 2 pi m over k by introducing this discrete gauge holonomy.
Sorry, so this just to understand this action, in terms of these complex coordinates Z1 and Z2, the Z1 is rotating with 2 pi by k phase, and Z2 is rotating with the minus of that or something like that.
Plus, I think essentially the
Same.
Yeah.
Same, that would not be any S2.
So it would be one of the two.
sorry, it should be sign one. Yeah,
Means it's a diagonal 2 pi.
yeah, essentially, minus.
Right, I thought if you take the two S2, one is J1 plus J2.
Yeah.
One will touch the Z1, Z2, and the other will touch Z1 bar Z2. So, by picking Z1, Z2, I already picked one of them.
Yeah, minus. Very minus.
I'm just saying this J1 plus J2 is the JZ or one of the two. Because J1 plus J2 and J2, J1 minus J2 are the JZs of the two S. Now you may be choosing the other S. There's nothing wrong with it.
So, okay, to be precise, if we say J1 has the 1-to-plane rotation
Yeah.
and J2 has the 3-to-plane rotation, this SU22 is J1 minus 3.
But that would have just, if you took J1 plus J2, it would have been the other S.
So now we turn on the discrete gauge holonomy, meaning that the
This is sometimes called as LKK.
LK1.
LK1.
So turning on discrete. Yeah, where was it? So we turned on the discrete gauge holonomy, meaning that the gamma invariant fields means that the geometric phase we get from the parallel transport and this charged phase should be equal. So the twisted state with J2 equals M will also contribute to the index on when you turn on this discrete gauge holonomy. And then since this is a gauge holonomy, you should sum over that to get the partition function. So we need to sum over all these possible discrete holonomy sectors given by the gauge group. And the index will have this schematic form. So here UAs are, as you have seen from the previous talks, nothing but the continuous gauge holonomy along the temporal circle. And this F is the single letter index at each discrete holonomy sector. So you basically get the contribution from the single letters after turning on the discrete holonomies, and you platistic exponentiate it to get the multi-particle partition function, and you project onto the gauge singlet by doing the Hermiter interval as before. So this is very similar to the index what you have seen in the previous talk, but the different thing is here that now you need to sum over the discrete holonomies.
So these holonomies lie, so you've got an SUN theory, right? So holonomies lie inside the diagonal. This SUN. Okay, so suppose you've got a holonomy in the first guy, then the things that are 1n, they are the ones that are charged under that.
One N?
1j.
What?
Look at a matrix. All our fields are geometry.
Yeah.
So the ij.
I 1 comma j component you're saying. That.
Yes.
Yeah.
Those are the ones that now will get this, will be allowed to have non-zero angular.
Yes.
And they all have charge 1.
Yeah. Also. Yeah. And here you see this prefactor, right? This is nothing but the supersymmetric Casimir range. So each sector will have non-trivial 0-point range, introducing the discrete holonomy sectors or the supersymmetric Casimir range. And in general, the theory will have unique vacuum, and turning on these non-trivial discrete holonomies will cost energies. But now I will show that this is not the case for the theories with n equals 4 supersymmetrics.
Sorry,
Yeah.
the blue for each set M alpha will be different.
You mean this?
Yes.
This is the wild group of unbroken gauge subgroup after introducing the gauge holonomies.
So it will be different for different
Different gauge holonomic types. Yeah. So if you don't introduce any gauge holonomies for SUN, this will be just n factorial. Yeah.
And delta NA is Van der Waals
Yeah. How measure Van der Waals?
for the unbroken SU.
Yeah. Right. You're right. Any questions about this second?
How do you compute Z0?
That I will explain. Any other? Great. So let me explain how to compute this Z0. Let me first start with the unrefined index for the simplicity. So you unrefine all the Fugacity sets in this way, then the index will have this form. And then if you compute the index and expand in terms of T at each holonomy sector, you will encounter this familiar state counting function, and in front of that you will have this prefactor, and this is nothing but the supersymmetric Casimir I mentioned. And this supersymmetric Casimir is nothing but analogous to the Casimir, but it is just, they are now just the index version, meaning that boson minus fermion. So they received contribution from the free oscillators which satisfy the BPS condition. and given as this. This is the charge we are counting. So, and obviously they will be divergent if you just sum over all them, so should be appropriately regularized. And the regulator function we'll use is today is nothing but the single letter index itself, because the single letter index is defined as the trace over this exponent for the free BPS letters, single letters. And if you just differentiate it with beta, you'll have this E0, right?
So where is this E0 coming from? Where do you have to do this regulatory index?
This is the definition of E0. And if you differentiate beta by this, and this exponent will come out. And you put beta, you take the limit beta to 0, then this will vanish, so you will have it.
But how do you calculate E0 to be that? The trace of minus
This one. This is nothing but the definition of Casimir energy. So basically, Casimir energy is nothing but the coming from the energy contribution from each oscillator modes, right? And now we are computing the index, not the energy, but this combination from the each single oscillator modes are what we want to compute.
That's for the usual index. Why don't we have this?
You have this. If you pass integral over 3 sphere, you can have this, but since you want some state counting interpretation, you just normalize, divide it and just divide it as
Casimir energy is sector dependent, flux dependent. So relative factors.
It's not an overall.
Yeah, not overall factor. So for the normal index, this is just overall factor. You just get rid of it. But since you have various sectors, so you need to compute it.
Will be independent.
Yeah.
And you're saying that is like just the 0 point energy.
Yeah.
So it's just 0 point energy per oscillator.
Yeah.
And it comes with -1 here.
Sorry.
Where Fermion goes on contribute differently.
Yeah, because we are computing the index. Our 0 point energy also have -1.
So where have you regularized this?
Sorry.
Where is the regularization procedure in this?
Yeah. Basically, we are using the single letter index calculator. So if you just naively summing over all the free oscillators, this will be divergent. I mean, you have infinite number of oscillators. Well. So you can use, familiar zeta function regularization if you wish, but here we have single letter index. This is more convenient.
The exponential is kind of a regulator.
Yeah. This is kind of regular.
So are you getting the, so let me go back like 1 or 2 Yeah, this expression is coming from the localization.
Yeah. Localization on this orbital sphere. Honestly speaking, this is the schematic form. No people considered about localization on S3 mode. Let's say E7 or something like that, but this is the schematic form.
But it's also what you get just for the free theory on this manifold, right?
Yeah. You just compute this wall of determinant and so on.
Yeah. So that's the other way. Just do calculating the free theory and it's independent of that.
Okay. And in that picture, how do you get Casimir energy?
You just pass the integral on the 3 sphere, then you will get the. In front of that, you will have this Casimir contribution.
Casimir energy comes from determinant.
Yeah.
So you do the free theory including the one with determinant. Okay. Because one with determinant is independent. Yeah. Okay. So that's part of.
Maybe I guess what you're asking from the counting point of view. How do you understand? Is there a Hilbert space way of understanding this expression?
I don't know about the state operator correspondence in these orbitals. That I don't know. Yeah, that I don't know. We are just counting states in these orbitals. Okay, then
Because operator would live at the singularity.
operator will be what?
If you consider state operator map, this would have to be on a 4-dimensional space which has been orbifolded.
Yeah.
And the orbifold X point is at the origin.
Yeah. Right.
And the state is on this S3.
Yeah.
And then as you shrink it back, you get an operator sitting at the singularity.
Yeah.
And then that becomes the tricky to
Right. And for the practical computation, let me start with the single letter index. This is the single letter index we have been seeing for the previous talks. So this coming from the holographic derivatives, and this coming from the single letter scalars, Carolinos, Gaugginos, and so on. And they are all joint representation under the gauge group.
So just following up on Abhijit's question. You could take the Lorentzian theory and you just look at all the modes of the Lorentzian theory. There is no holonomy because now time is not periodic. And then you could try to compute the trace in the Lorentzian theory imposing Gauss law. That feels like a slightly different reorganization of this calculation. Can you see how it works?
Not necessarily using the state operator correspondence, but
just on this manifold.
Just on the space. In principle, you can compare the theory.
Shouldn't be too tough. I was just wondering somehow Gauss law model. It's not, this. But what is these holonomies? What is the Lorentzian?
Well, this is pure. Well, this doesn't have to do with time circles, so yeah.
Oh, it doesn't. It's just holonomy in this space. Okay, then it's just straightforward.
Yeah.
Okay, please go.
No, but what do you mean straightforward?
Meaning you will just include all modes, but including holonomies.
Right.
You'll have various sectors of your theory.
Okay.
Each sector will give you, sector will be labeled by holonomy. Now you expand your fields in that sector. And then you get modes.
Right.
And then the sum over these holonomies is just sum over sectors.
So in each sector, you should get some integer counting.
Yeah, that's true.
And from that point of view, the 0 point energy is just standard 0 point energy.
And from this single letter index, you can read off some.
Sorry, I'm just trying to understand from this point of view the 0 point energy, the relation of that and integer. Whether it's quite integer and counting with the 0 point energy.
You just shift the energies in that sector.
You can shift it. Right.
Yeah, overall factor is not important.
Yeah.
It's just shift of the 0 point in at each sector.
Yes.
So from the single letter index, you can read off this representation structure of free BPS fields. You have adjoint representation in the gauge group, and the V is nothing.
So these are like twisted sectors and all.
Yeah, twist sector.
Basically.
Twist sector.
So many sectors of it. It's just that.
This V is nothing but the two-dimensional representation, and Sn is the n-symmetric power of that. Two-dimensional representation of SU2 and n-symmetric power of that. And we now want to account for the single letter index on S3 mod gamma, introducing discrete gauge holonomy. And then it will receive contribution only from gamma invariant field, as I said. And basically, you introduce the projector onto the singlet under the gamma action.
So just to get orientation, is the expectation that you're going to match with black holes whose area will be modeled basically 1/n of the area of this?
Today I will not talk about black.
Okay.
But if you go to the deconfining phase, that will be true.
So the area of the corresponding black hole will be just, if you took the ZN mode, it's just 1/n of the.
Yeah, that's true.
So you should get this high energy behavior, just 1/n of that.
Yeah, that's
Even before black hole,
sir.
Even before black holes, I mean, this matching of gravitons seems a bit non-trivial. But you will do that. You will have bulk correspondence later on.
Yeah, today I will only focus on vacuum set. You will see.
Okay.
But the bulk geometry is singular, right?
Yeah.
If there is no black holes.
Yeah, there's no black.
Yeah.
So you will have to account for possible twisted sector states then?
Yeah, singularity, you will consider some twisted sector.
Yeah, so, and you know, the fact that the ordinary case it just matched with the graviton was kind of straightforward, right? But here seems a bit non-trivial, right? How these sectors match up.
Yes. Yeah, that is very not trivial, and that is why I want to share with you.
Yeah.
So the singularity index on S3 mod gamma get contribution from only gamma invariant fields. So you now introduce projector. This is nothing but you can think of it as discrete version of Hermitian integral. So you act this projector on this vector space and take trace to get the singularity index. And you have this expression. Rho V is nothing but the two-dimensional representation of gamma here. And when you go from here to here, basically this lambda is nothing but the lambda and lambda bar, nothing but the two eigenvalues of this 2x2 matrix. So basically you are doing plasticity exponentiation in your standard index computation. So you got this expression. The rho G is the discrete cage holonomy we turned on. And as said, the supersymmetric Casimir energy is proportional to the derivative and taking the beta zero. And if you consider non-trivial element of this finite subgroup, then it will have non-trivial eigenvalues. And meaning that if you expand this in terms of beta, where t is e to the minus beta, it will give you order of beta square contribution. But when meaning that you do not turn on the gauge holonomies, then lambda and lambda by equals 1, and this will give you order of beta contribution. Meaning that while you are summing over all the discrete gauge holonomies, only the trivial sector contribute to the supersymmetric Casimir. So the Casimir is independent of introducing discrete holonomies. It's just some number. This is overall vector, so you can just get rid of. And I should emphasize that this is purely n equals 4 supersymmetry effect. So basically, you're working with many supersymmetries. So bosonic and fermionic contributions cancels each other magically, and the supersymmetric Casimir is just gone. But if you consider generic theories with n equals 1 supersymmetry, of course, it will have unit vacuum. The supersymmetric Casimir will depend on the sector. However, for n equals 4, for arbitrary gauge group, for arbitrary orbifold, this will be just the same. So you can ignore this supersymmetric Casimir. And you may ask, can you have more other non-trivial example? People have considered some class S series of type class S series for some limited case. Basically, this is nothing but M5 brane wrapping some Riemann surface. n equals 4 family is M5 brane wrapping torus, but you can consider some non-trivial Riemann surface. And in this case, you can show that actually not all the Casimir energy is the same, but at some sectors, you have the same Casimir energy, and they form ground states of the theory. And for the other sectors, the supersymmetric Casimir energy is higher, and they contribute to the excited states of the theory.
Well, I mean, these are different superselection sectors, right?
Sorry?
Aren't these different superselection sectors? They were labeled by different belongings.
Yeah, they don't touch each other, so.
Yeah, so in that sense, you have multiple ground states reaching up. And in this notebook, I'm just, I guess, complaining about the nomenclature. That the states with first Casimir energy is a ground state, and the sectors with first Casimir energy are the ground states, and sectors with the higher ones are excited. Those are also ground state in that sector.
Yeah, that's true, but in full Hilbert space. So basically, this is gauge element. So you should sum over to get gauging them for Hilbert space.
I suppose Abhijit's asking, are there operators with matrix elements between one and the other? Are there,
Yeah, that I agree.
what are some Wilson lines? There. Maybe it's something that changes the Wilson line. What changes the Wilson line like an electric moment? There may be.
And there are some actions from one random state to other random state, and actually that is what I want to explain.
Oh,
So for n equals 4, anyway, we now have large number of degenerate vacuum to be found. And these vacuum states are labeled by, as I said, discrete holonomies. And for now, for simplicity, let us consider the case with unitary group case. And basically finding discrete holonomies is finding the map from this finite group to gauge group, and each such group can be specified as irreducible decomposition. Let us call rho I as the irreducible decomposition of gamma, and general representation is parameterized by non-negative integers like this. Ni times dimension of this irreducible representation, and you should sum. And if it equals n, it will give you some map from gamma to G, meaning that you have found some discrete holonomies. And following the Mackay, we draw the diagram for irreducible representation of gamma. So these numbers are the dimensions of each irreducible representation. Each node is represent irreducible representation of gamma. And of course, it is already well known, but if you see this diagram, you know that this is nothing but the extended thinking diagram of compact Lie group, right?
wait, suppose we're just doing SUN. Then it's just the number of the holonomies in each eigenvalue, each diagonal, right? And then you can kind of block them together with how many have 1, how many have 2.
No.
If you're doing ZX, but that's been it's always sticking to SUN.
Oh,
The question is what is
Z, yes, Z.
Yeah, then it's a usually one dimensional always.
Yeah.
Given by the charge. And
Yeah.
dim row would always be 1. So as you said,
Yeah,
1
yeah.
plus n2.
Yeah.
Summing to n.
So you will have some n1 plus n2 plus n3 plus n4 equals n.
Go ahead, now. Okay.
And this is nothing but the extended thinking diagram of compact Lie group. And if you're familiar with Chern-Simons theory, you can think of it as actually the states of Chern-Simons theory. So states of pure Chern-Simons theory with gauge group now given by the compact Lie group, AD type, given by the Mackay correspondence at level n on torus is given by reducible representation of alpha in Lie algebra and parameterized by non-negative integers. This Mi is now the comark for the Lie group, and we know that by Mackay, these two integers are the same, meaning that we have found the vacua, the one-to-one correspondence between vacua of n equals 4 un supertriangle zone S remote gamma and the vacua of G gamma Chern-Simons theory at level n on the torus.
There are increasing quite on that kind of funding.
Yeah, that is I will gonna explain now.
What is that group G gamma?
ADE, the classical group. SUN, SO2N, E6, E7.
Oh, I see. So you take the irreps of the affine Lie algebra of whatever AD group at level n and take Chern-Simons theory corresponding to that on T2, and then there's a one-to-one correspondence.
Yeah. So basically, you have some finite subgroup here doing the orbifold n equals 4 triangle, and then on the other side, you have this compact Lie group by the Mackay correspondence, and you have Chern-Simons theory with that gauge group at level n on the torus.
So is the time circle of the n equal to 4 super angles taken to be 0.6?
No. I just wrote down the specials manifold where you have of course time circle.
So just to spell this out, many Zn case, then on the one left hand side you have these
SUN. No, SUK. ZK SU4.
Right. But on the left hand side you have this N1 plus N2 plus blah 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 equal to a capital N.
Yeah.
Right. You can imagine Young diagrams of that. And over here, of course, you will have Young diagrams there, right? Some level N.
And these N1s are all less than K.
Right.
Yeah. Right. So we found nice mathematical map between these two. And I want to explain this duality from string theory, AdS correspondence. And before going that, I will explain one interesting application of this duality. So you can generalize this to other gauge group of n equals cross families. Of course, SO, SP, you need to think a bit more about some funny mathematical object. But anyway, you can do that. And then you can, yeah.
Coming back to that. So these are now the integrable representations of SU K level and SU M.
The height is always less than K.
I was thinking the width, height is on, yeah.
But the N seems to be the total number of boxes, not the width.
Yeah, total. You should sum over them and it will give you height.
Wait, yeah.
So this is from the M5 grade, I would imagine, right? M5 grade or Taurus.
Yeah, right. You can also think of it as that way.
So the prediction also for the classes.
Yeah, sorry, and just to say again for the ZK case, what is the various twisted sectors and one-to-one correspondence with what?
If gamma is ZK and you have SUK Chern-Simons theory at level N.
SUK Chern-Simons theory at level N.
On the torus.
So SUK Chern-Simons theory is the representations are labeled by Young-Pavlov whose rows are not larger than K. Right? No, rows are not larger than H. Yes.
Oh, yeah, level is N plus.
Now this is not larger than N. Where is that coming from?
This function.
Oh, because number of boxes, total number of boxes is nice.
That doesn't seem to match exactly.
Yeah.
Wait, what was your problem?
If you count the twisted sectors, they're just labeled by how many guys have twist 1, how many guys have how many guys have twist 0, how many guys have twist 1, how many guys have twist 2, up to how many guys have twist K minus 1. Right?
Yeah.
We're trying to make a Young tableau out of that. I mean, SUK at level N is labeled by Young tableau with at most K rows and at most N columns. And how do you make that?
That's right.
So how do you map that to Young tableau?
Total number is N.
No, but the Young tableau should have the property that the height is always less than K and the width is less than N.
Yeah, I mean, maybe I draw in the reverse direction. This should be K less than K.
The number of twists cannot be more.
Yeah. And this will be less than N.
Will obviously be less than N because the total is N.
Yes.
Well, that's one-sided correspondence, but here, for example, if you consider a rectangle of size, you will get more
From the integrable representations of SU K level, and you get more because you can have more than N box.
more than N boxes.
But we get up to NK box.
But here, the total number of boxes should be N.
That's the problem.
On the right-hand side, when you look at the Chern-Simons theory at level N, SUK Chern-Simons theory, vacuum of that, there will be a vacuum, which is a big rectangular box of roughly N by K size. Maybe N minus 1, K minus 1, whatever. So on the order NK.
Yeah.
Maybe there's some different labeling, which I'm ready to.
It feels a little bit like N is more like intense. On T2, maybe that's not the same as integrable representation. It's a
Because you can have a similar code, right?
So we can come back.
Yeah, maybe we can discuss later. I thought that this is the correct example. So yeah, we have some interesting implication of this. So now we have degenerate vector. So you can now ask what kind non-trivial and you can test the
Sorry, I think I understand. N1 is the number of columns of a particular height.
Yeah.
N2 is the number of columns of a particular height.
and one kind.
Yeah. No.
Oh, I see.
N1 is the number of columns of height, let's say k. And then N2 is the number of columns of height k minus 1. Right? And then that will work out. Right? N has a subscript which is less than k, right?
Yeah,
So
sure.
N1 is the number of boxes of size of height k.
Yeah.
And Nj is the number of boxes of height j, let's say. Yeah, that will work. Yes, the correspondence.
Yeah. Okay.
Yeah, sorry, I misunderstood, but yeah. But that will work, right?
Yeah.
And the height will be that. It will be, yeah.
So yeah, sorry, maybe I used some language. Okay, then we can have some non-trivial agility checks on this degenerate vacuum. So let us call the number of degenerate vacuum as n gamma g. And the agility will map between these two SDL groups. And if the theory has some one-form symmetry, and vector will be leveled by discrete holonomies are charged under these one-form symmetries. So if the vacuum this vacuum is charged under electric and magnetic one-form symmetries, then under S duality, you change the gauge group to the S dual group, and also you exchange the electric and magnetic symmetry. So for the unitary group case, the theory has U1 electric and U1 magnetic one-form symmetries. And on S3 mode gamma, they act on ZK. And vacuum leveled by discrete holonomies are charged under ZK.
But this is a bit fast. Can you go back to the previous slide? I want to understand this again.
You change G to G tilde, SDL group, and also exchange the electric and magnetic symmetry.
N is this number that we are talking about?
Yeah, number of vacuum.
E and M are one form symmetries.
Yeah, so number of vacuum whose charges are E and M.
Right.
And that will correspond to the number of vacuum for the SDL group whose charges are M and E.
And gamma is unaffected.
Yes, gamma is not. Yes. So for the unitary group case, you have U1 electric and U1 magnetic. And the one-form symmetry group is ZK. So this E and M are ZK value. You have 0 to K minus 1. And of course, UN is self-dual. So you can check that this refined number of vacuum is matched under the S-duality action.
Sorry. Can you say a little bit more about these charges E and M? So if I've got some sector with some in ZK example, if I have some charges in the K holonomy sector, Mth holonomy sector. Now that carries some electric charge and some magnetic charge. What electric charge?
Basically, they are Wilson lines, so you can consider some one-form symmetries acting on them, right?
One form symmetry is a bit hazy about, but just tell me a little bit, where is the magnetic part? This Wilson line sounds electric.
Yeah, Wilson line.
Is it that, so you have, on the S3, if I think of it as a S2 base, your Wilson lines will go across the S2. So that, if you were using transition functions, you have to cut the Wilson line at one point. And you exchange that with Toft lines from the class. Just ask.
Yeah, that's true.
But had you put it, I thought so far we were talking about just Wilson lines. Did you have some Toft lines in your story?
Don't you have to? Or no?
So far what he was talking about was just Wilson lines. So,
Yeah. He could have followed me.
No. In this case, if it
Time is not playing. But if you take one side, which is just Wilson line, then you go to the other side, won't you have to put the magnetic lines? That's
that's what Sunjin suggested. But so far we've not done that, right? Oh, are we going to do something new then?
no.
Why not do the original self into a group and you can't talk about
So do some things where you have you use non-single gauge transformation. So that's now like an operator in the theory. Here it could not naturally appear in the path index, whereas this will or all these gauge configurations will appear. But I understand this very good.
Maybe you can give an example like this is just ZK example, right? Where you have these sectors labeled by these integers, as you said. Now, for each sector, what is the value of N and M as the electric and the magnetic that you will assign, so that we know how this assignment is done.
Yeah, that is true, but yeah, maybe I can show you later about this part. Actually, I just as funny, interesting implication from this paper, but yeah.
Okay, it will not going to play a role, I guess.
Yeah. Or you can consider some. I think this will be more easier to understand. You can consider some SPN series or S1 series or S3 model E7, but anyway, this theory will have Z2 one-form symmetry, meaning that you can decompose the states in the Hilbert space into the states that are even or odd under the interaction. And you can twist the Hilbert space by Z2 one-form symmetry. And in fact, of these two are exchanged under the S duality. And you can directly check from the detailed computation. And actually, this is expected from the S dual pairs of involving Z2 gazing between SO2n plus 1, SPN, and spin group, and SPN also.
Just one last, along the lines of what Sandeep was asking, if you think of this S1 as like fiber over an S2, then one sort of half natural thing you could do is include fluxes on the S. Is that part of your story?
All not turn on the flux.
Okay.
But path integral should not turn on flux because you now have a non-trivial cycle there, right? Two cycle. In a way, for example, when one computes index in 3 dimensions, one has this S2 in the game, and then one sums of fluxes. What happens to that?
Okay, let me explain this way. So we introduce various sectors parameterized discrete polynomial, and if you increase the degree, let's say zk, and consider the case of infinity limit, and this discrete polynomial sector is nothing but the monopoly flux sector. So you basically sum over the monopoly flux.
So it alternatively can be understood as a
Flux on S set. Yeah.
Because of this
duality. Yeah. So you can also understand as the flux, turning on the flux on it.
Maybe non-trivial gauge transformations can sometimes be understood as flux, like in the, the transition of the,
Like a monopole.
Yeah. So I mean, the natural thing is if you take, sorry, I mean,
No, please,
if you
please.
take the S2 and you break it into, and you have a non-trivial transition function, because the S1 is non-trivial fiber. You can also do a non-trivial this gauge transformation in the S2, just connecting. I mean, what are the rules for the path integral? It's not fully clear.
Yeah, like what bundles do we need to?
Yeah. You will.
I would very happy to.
And you might want to.
But are you saying that this is an alternate description of this holonomy sectors? Or it's a
I was
different?
thinking those non-trivial gauge transformations are the analog of monopoles. So maybe I'm wrong. This,
No, but I think what Keith was saying just now is that the K going to infinity limit, where this you can think of that circle just going away, because you just not put it away. Then you get index of 3 dimensions.
Yeah,
And there we know that there is a flux sector that we have to sum over. And he's saying that these holonomy sectors that we just introduced here, which had to do with that circle that went away, becomes
monopole flux,
monopole flux sector.
honest.
Maybe too much application. So let me explain now the origin of this duality between spray-Yang-Mills and Chern-Simons theory using AdS response. So we start with n equals 4 UN for Yang-Mills on S3 mod gamma. We have 3 parameters, n, and tooth coupling, and complexified gauge coupling. And in the dual bulk side, we have 2B string theory on AdS5 mod gamma times S5. Today we always focus on the confined phase. So AdS5 times gamma has the topology as time times 4 ball mod by gamma. And the fixed point will be at the origin. And as usual, the string coupling and string lengths and the exterior dilaton will be mapped to these parameters. And also, you should note that there exist n units of R5 envelopes on S5. And you do the T dualize to 2A along the whole fiber circle of S5. And you will get, so then this will be the trivial bundle getting the CP2 times S1. And also you introduce some NS3 form flux on top of that, because you have non-trivial bundle and the chunkless will be transformed to the NS3 form flux here. But this effect of this NS3 form flux will not be important in our discussion.
By the way, when you're doing this T-dualizing the Hopf circle of S5, the Hopf circle is not like
On contract.
yeah. So is that move relevant?
You can also consider some T-dual along this non-trivial circle, whole fiber circle. And the effect of it is that you introduce some NS3 form flux on the other side.
I think his question was that because it's not because this thing is not non-contractile, some point it shrinks to 0.
Mm-hmm.
So I mean, you get so momentum is no longer conserved.
Mm-hmm.
Therefore, on the other side, winding will no longer be conserved. And he's trying to ask how that will come about. You know, there's usually trouble when you try to T-dualize on a circle that is somewhere.
Well, actually, this is whole fiber circle, and momentum is conserved. Momentum is conserved.
Momentum is conserved. Momentum is conserved. Let's say we've got a circle that shrinks to 0 somewhere. Then, yeah, you're right. Winding is not conserved here, so momentum will not be conserved on the other side. Maybe that's the H flux.
Yeah, here we have H flux.
Also, if a circle shrinks to 0, we get infinite coupling. Then you do the description.
No, in the T-dual, you don't have, well, this is a trivial circle, so it doesn't shrink in the T-dual. So,
No, but in the original size shrinks to 0.
Yeah, that's
The
right.
T-dual description has infinite coupling. Because the dilaton transforms under T-dual.
Yeah.
Okay, anyway, done.
Yeah. And also you have R4 form flux on CP2 because you T-dualize it. and you have the two-way coupling and RR potential.
In particular, you say coupling is dependent on space dependent. But this is
Now we create somehow this fiber circle which is constant size, whatever that. I mean, there's some topology. I think it will not. Yeah. That's something you can do.
and also after duality just becomes a trivial product.
Yeah, trivial one.
One just follows Busher rules.
Yeah. That's what I'm doing here. And you only to M theory. And M theory circle and TDOI circle will make a torus, and the complex modulus of torus is equal to tau. And now M theory background is time times 4-ball mode gamma times CP2 times torus. And we have 4-point flux on CP2. And now I want to focus on localized degrees of freedom and fixed point of this orbit fold. And geometry near such a fixed point is time times alpha mod gamma times CP2 times T2. And it is famously known that near such a singularity, we have 7-dimensional maximum supersymmetric gauge theory probing this transverse space. And the gauge group will be given by the Mackay correspondence. So if it is ZK, you will have SUK gauge.
Before, what would B4? B4?
D4.
B4.
4-ball. 4-ball.
4-ball.
Yeah. I'm just talking about topology. And near the fixed point, you can think of it as just an R4. And
if gamma is let's say a trivial thing, then what is the Mackay correspondence?
some trivial, you mean normal people?
No one.
But nothing. I mean, nothing and nothing.
But you still have something on the you have 40 and equal to 4 superangles on S3.
Yeah, then you'll have AdS5 times S5 to be.
No, but there was something Chern-Simons there.
Yeah, only when you introduce the orbifold, then you have degenerate vacuum. That is explained by Chern-Simons theory. But if you don't introduce orbifold, we have unique vacuum.
So if you didn't do the duality, you would have just got R4 mod gamma times S5, right?
R4 mod gamma times S5. On what circle you do the TDO?
No, don't do it.
Then what? Sorry, then what?
Then you just look at the near the.
I need to be side.
Yeah, on the two side.
Yeah.
It's just R4 mod gamma times S5. And so you're replacing that S5, R4 mod gamma times S1 times S5. Right, because the S1 will be.
Yeah.
So that S1 is going around for the right, and then you've got the fiber S1 of the S5. You're combining that into a torus up equilibrium.
Yeah, right.
And so you needed this duality because you wanted this correspondence with, you wanted the statement that you know what happens at such singularity.
Yeah.
Okay.
I'm sorry, the end units of 4-form flux don't enter in the second part of in the map to the SU Suzy gauge theory, is it?
That will encounter the action of the seven-dimensional gauge theory. So in order to see detail about the seven-dimensional space,
if you just take R4 mod gamma times S5, that is not a solution to Einstein's equations, right? Because you've taken AdS and replaced it by R4.
Yeah, R4 is not, sure.
So this is just topologically.
Yeah.
But
Near the singularity.
But then near the singularity, you should also replace S5 by just R5.
No. We just focus on near the singularity. The complex space is the transverse space.
I mean, it should be working with solutions of Einstein's equation. In AdS5 times S5, the negative cosmological constant of S5, of AdS5, and the curvature of S5 balance each other to make a solution. Now, it feels like what you've done is just replace AdS5 times S1 by flat space, but not done the same with AdS5.
Yeah.
And then that will no longer be a solution.
Yes.
That doesn't worry you.
We are just talking about the localized degrees of freedom near the singularity and what happens to that. I want to focus on the brains wrapping the singularity and ignoring the effect of curvature in AdS5, but that will probe the internal speed. Right.
Do they go around they're very localized on the AdS5, but they go around the
yes, right.
I see. Because they're twisted sectors?
Yeah, right.
Literally uplifting to M theory should have given you a solution to the M theory equations, right? With a four-form flux and so on. Maybe up to the breakdown of the orbifold. Yeah. At least so the first part of your slide does give you some solution to the M theory and so on. Yeah. And then
Then is it near focusing on like tangent space around the orbifold in the AdS, but keeping the full distance in the internal space.
So of course, in this M theory background, there will be this degrees of freedom on full 11 geometries, but I want to just focus on the twisted sector at the fixed point, exploring this internal surface.
right. So actually, the first part may not have been quite before mod gamma, but because you just look at that vicinity.
Yes, topology, and it will give you R4.
And then or is it?
The first part is before which system come before, but then the approximation is the R4.
Yeah, R4.
Okay, that's it. Yeah, okay.
And we resolve this singularity of B, then compactify M theory on the Taubman circle of this gamma orbifold. And you will have K D6 rings wrapping the transverse space, right? And you have N units of 4-point blocks on CP2 as before. And we want to see these low energy dynamics of KD6 rings.
Where did the D6 rings come from? Just say one content.
You have singularity here, let's say ZK. Okay. ZK, and resolve the singularity of it by holographic monopoles, multi-center holographic monopoles, and you do the compactification on the Taubman circle, which will give you the KD6 rings. And you have N units of R 4-point blocks on CP2 as before. And the low energy dynamics of D6 branes are governed by Dirac-Bonnet tension plus best terminal. And our degenerate vacua will be coming from the best terminal action. So here you have this term. This term. And well, just expanding this, you will find this FHC3 integrate out. You have Trans-Simons 3 form times 4 form. And you integrate that 4 form on CP2. It will give you N. And you can carefully fix all the normalization coefficient. We'll have Trans-Simons theory at level N on the torus. This is the torus I get from this absolute and TDO. So you have the 3D pure Trans-Simons theory of, let's say, SUK at level N on the torus.
You say that there is a correspondence with, the vacuum of Trans-Simons SUK at level N, but you could have said SUN at level K also. People would have been fine. Well, no, I say that because if I kind of take the M5 brane route, I seem to be naturally landing on SUN at level K. Because I have N equals 4, I make it from M5 brane as torus compactification.
Yeah, you can think also in that way. M5 brane on and M5 brane on torus times 3 mod ZK times chi.
Right. Exactly. So now you compactify M5 branes on S3 mod ZK. Otherwise, you get SU, and you get a gauge rank, right? Because the N is the number of gauge. You get SUN at level K. And you just get SUN at level K Trans-Simons on T2 times time. So you get states on T2. This point of view then gives you more because then T2 could have been anything you want. So then you will get clocks. Something that one can check with the S classes things.
Maybe that is another way of another duality between transcendence.
But the form it comes is SU at that level.
Yeah.
So in this picture, M5 and M5 rate that you take turns and will be a supersymmetric transcendence that we have.
This is pure transcendence.
But what if I compactify this M5 rate on S3 mod ZK, I'll get a supersymmetric low energy state.
So it is.
Yeah, I compactify on S3 mod ZK, so I get a resulting T2 process completely.
Well, you have just pure transcendence.
So maybe given that this is not his main point.
And so we have found the string theory origin of this duality. And now I want to talk about one-form symmetry action. So we have type intended following type 2B coupling, F5 wedge B2 wedge DC2. If you interpolate F5 on S5, you'll have this section. And actually, this is nothing but a mixed anomaly between ion electric and magnetic one-form symmetries of n equals for UN supply mills. So you can think of it as this B2 and C2 in string theory will serve as the background two-form field for one-form symmetries of n equals for supply mills. And in 2A, this will become B2 and C3. And in M theory, this becomes C3. They become all M theory 3 form, and they have a leg on the torus. And here dx1 and dx2 are nothing but the cycle along the A and B cycle. And you now want to understand this one-form symmetry from the 70 gauge theory, focusing on the effect of gamma ripple. And you know that M2 grains wrapping compact cycles at the fixed point will give you double bosons of 70 gauge theory.
You say that last sentence again?
M2 grains wrapping compact cycles at the fixed point
Yes.
will give you double bosons of 70 gauge theory. And also, you can consider M2 grains wrapping non-compact cycle, radial direction, and whose one cycles will end will probe this obifolded circle of S3, or fiber circle of S3. And this will introduce line operators of 70 gauge series. And you can consider two types of line operators in 3D transassignment theory, basically wrapping A cycle and B cycles on T2. And this A and B cycle Wilson line will be dual to electric magnetic one-form symmetries of 40 equals 4 square mills. So yeah, this background field for one-form symmetry of 70 gauge theory will be given by the boundary value of this M theory 3 form, and that is dual to the U1 one-form symmetries of n equals 4 square. And here is the map. You start from n equals 4 square mills and vacuum states are parameterized by discrete holonomy. You can add SL to Z duality and you have one-form symmetries. And these two factors are exchanged by the S duality. And in the dual side, let's say gamma equals K, then in the dual side, you have 3D SUK transassignment serial level and T2. And now this SL to Z duality is realized as geometric action of SL to Z on the torus. And S duality exchange the A cycle, this SL to Z geometry action exchanged A cycle and B cycle of the torus. And this is nothing but the dual to the S duality acting on these electric magnetic forms.
This is really complicated. I had thought you would do something really simple. I had thought that you've got this orbifold in the boundary that makes an orbifold in the bulk, and you have closed string twisted sectors. There, and that would match all your states. That doesn't work. Just R4 mod, whatever, ZK. Just look at the twisted sectors, the close strings, and are there one-to-one correspondence with your R?
But I think the main point is the S1, right? Rather than the.
Yeah, twist sector match, and I'm talking about the twist sector. I'm talking about each ground state of the twist sector does match.
But sorry, maybe I'm just completely misunderstood. But I thought that you were trying to explain the number of holonomy states you got from the boundary counting by number of states and some deviations.
Yeah.
I thought that would work in a different way, or maybe an equivalent but different way, which is just counting number of close string twisted sector states, which is close string all over. Sorry, it's very good question.
Is the problem that if you try to do it in the starting 2B or 2A, you have to face up to the number?
Yeah, well, yeah, that's true. Yeah. If you started from 2B, actually you will have some 6220 series coupled to R5 complex, which I don't know how to do.
But okay, let's say I'm taking a very large radius to start. Then, like you do, right? You just focus on this neighborhood of the R4 of the orbifold. Then you can forget everything else. You're forgetting curvature, so you forget the flux. And then it's just 2B in flat space.
No, flux is on S5, complex sphere. You cannot get rid of.
It's also a flux on AdS5. I'm saying just the R4 part. Just the AdS5 part, you replace that by flat space. That I thought was what you were doing. So for the orbifold part of it, you're just working with flat space string theory.
The orbifold part, you have twisted sector.
Okay.
And that will explore along the internal sphere.
Okay, it explores on the internal sphere. So first, just for the R4 mod, whatever, ZK, there you can just count all the supersymmetric twisted states. And then you put them in some momentum of the S5. Is that what's happening?
Yeah, you count the twisted sector.
So those guys, and then they can also move around on the S5. Is that roughly what's?
Yeah. But I'm saying that this 5 flux on S5 changes this number of twist sectors and this thing very much.
Oh. Okay. I thought the only string theory you would have to do is in the neighborhood of this orbifold, which anyway you were replacing by R4. So there I would just do that very simply.
That's true.
But the rest will be just super random because it's big.
Yeah, I thought so, but somehow we realized that the interspace flux affect the twisted sector.
Okay. Yeah, I need those.
And that give you this degenerate.
The final answer you got will depend on n in some non-trivial way. I through at least the level something like that. So your final answer depended when you map to 3D churn samples, how is the level n there?
Yeah, right.
Maybe there's a subtlety in taking n moving.
What happens when you take entry there? In that limit,
That's
yeah.
And to infinity. Well,
then does it just become very simple? N was a level. I can think of n as level of churn samples.
Yeah.
Okay, great. So then it simplifies, right? You get classical group theory. You've got your states are classical S2K. I don't know why it's. I don't know why. And if you just did close string orbifold, just the twisted sectors R4 or ZK, what does that match? Does that match in?
I mean, just to make it a proper string background, you have in mind R4 mod ZK cross R6.
Right?
That's what you mean, right?
You mean T6 or something like that? Yeah, so R6. Yeah, R6. Yeah, R6. Okay. But what I want to emphasize that
But even in the n goes to infinity limit, it should more or less be right? Because basically that's what you're doing. You're taking something which is part of a complicated geometry and focusing only on some tangent space.
But well, if n goes to infinity, meaning that the flux goes to infinity, right?
Yes, the size of the sphere also goes to infinity. It's basically well approximated locally by flat space. I mean, and lambda is large. Nothing depends on lambda.
Yeah, nothing.
Okay, I probably very stupid questions.
Yeah, actually, original reason why we started this problem is that, so if we just consider 2B theory on this space, you have singularity on the origin, meaning that you will have 62-0 theory on the transport space, right? This geometric engineering. So we thought that we can compute some 62-0 theory superconformal index on S5 times S1. But now the problem is that we have R5 on flux. So if it is just ordinary sphere times S1, then you'll have superconformal index, you'll have unique vacuum. But now we learn that if you have R5 on flux on this internal 5 sphere, you have degenerate vacua and the situation becomes more complicated. And yeah, so if you consider the simplest case, ZK case, you can consider the large n limit, let's say n equals to infinity limit, and compute the index at each holonomy sector. Give you this. And you can consider the spectroscopy index from K-Causa-Klein modes, quoting this can be AdS5 both ZK times S5. And this give you just this.
From untwisted.
Yeah, untwisted sector. Just so exploring all candy space.
So just when you say large n, the sectors are labeled by the L1, L2, and so on, right? You're taking all of them large.
Yeah, here in this sector, you will have all of them large as order of n, or you can consider just running only one a discrete holonomy and take this to be n and go to n equals n.
Okay. Okay. It doesn't depend on these ratios, right? It just the same, no matter what the ratio, as long as they're large.
Yeah.
And then you said the match with these gravitons. So what did you say? Okay, you compute these.
You compute these gravitons, and we see this doesn't match.
It does not. Okay,
It does not match. So we need to there's basically because we have some twisted string modes in this orbital singularity. And in this paper, they have some suggestion about these holonomy sectors in the gravity side. So when you have these discrete holonomies, you can consider it as some distance between K and S5 branes on the structure. And in this case, you have equally spaced NS5 branes. And in this case, you have coincident NS5 branes, which means that the twisted string modes at the singularity will become more important maybe in this sector. So yeah, I mean, I was wondering if one can understand this as some twisted string modes of 60 theory and 60 theory. So this is just technical part about excited.
So if I consider these untwisted gravitons, right, in the bulk, right, just invariant under the numbers, is there a proposal about what it should match with on the theory side?
AdS side.
AdS
theory side. No.
Is it not the one where you just have N0 turned on and nothing else?
No. It doesn't match with any
sector. Okay. Yeah, so this is kind of confusing. So there are so many sectors, right? And then here we are looking at the sectors where all of these are large, right? And the ratios are perhaps kept fixed. But there are also sectors where some are small, right? Like order 1. All numbers are order 1, and one of them is large. things like that. And that is very quantum, right? I mean, the kind of expression that you get for the index is a U2 integral, U3 integral, and so on, very quantum things. So how is it ever expected to match from something that is a purely gravitational description in the bulk? How will it be matched?
Yeah.
I mean, even a rough idea. Because on the gravity, okay, we are doing this orbifold, but not like n, there is some section where n is small, right? That there is some quantumness to this gravity. So I was wondering, how are these very quantum sectors going to match in any sort of classical calculation in the bulk?
Or that I don't know. I'm not sure whether there can be a quantified twist for.
So what would you have to do?
Maybe you get some. Sorry, I don't.
Sorry, one more probably. So, even in the zero twisted sector, you've got this orbifold in the back. Because that's just the geometry.
Yeah.
Now, when you turn on a twist on the boundary, how does that change the bulk?
Twist on the when you turn on the discrete gauge holonomy, what happens?
What is the change? What is the effect on the bulk? Like, is that some holonomy of B? You can't see it in the bulk.
At the moment, I cannot see such in the bulk.
You can't see it.
Yeah, I cannot see the bulk.
Is there some gauge invariant operator on the boundary that knows that there is a twist turned on?
Gauge invariant operator knows that is the twist.
That can distinguish from you being from a twisted holonomy and non-twist. If so, we could then use the AdS-CFT map to find out what the change in the bulk. So every gauge invariant operator we can follow to the bulk.
So is it not the representation of this UN part, ZL part, space action, orbifold action? This geometric orbifold action, and this sector, when you say K, it's telling you that the states are a charge K under the ZL.
Under what again?
This some rotational ZL, right, under which you are doing now.
You mean? Yeah.
So
you can, maybe
one of that,
that
you look at the states which have that particular charge in the bulk. But it is, clearly it's not matching, right? I mean, there is some
and it was linked also to the charge.
gauge.
Gauge charge.
Yeah.
So you want some gauge invariant units.
It's not Wilson.
Yes. The sector is basically turning on the Wilson line on gauges for this circle.
Yeah, the other probably very stupid bit is the question is that you've got this S1 now in your let's say you've done the ZK. So you've got some non-contractible cycle here on your base. But you're mapping that into some holonomy on in SUN. And in SUN, there are no non-trivial circles.
No.
So this is some localization kind of thing, or is there some topology protecting these sectors? Can I go continuously from a sector with charge 1 to a sector with charge 0?
No.
I cannot.
No, you can't.
Okay, so it's topologically protected. So then there should be some clear way of.
There should be. Actually. I also always wondering whether we can see this discrete holonomy from the bulk, but at the moment we don't know.
it is now complicated, right? Because of this, because the sector could have a very small amount of N can be very small there. So even for Z2, you have N0 and N1, you could have N0 very small and N1 very large. And that N0, the way it contributes to index is like U3, U4 integral. Right. Now, how can this come out from anything? It's probably not a very simple description.
That's what the puzzle. I mean, yeah. So, yeah, basically, yeah, we don't understand it very much. So far, we just count the vacuum and batch branches. So, yeah, let me just summarize. So we studied protein equals first family on S3 mod gamma. So I explained to you that the stochastic vanishes for every sector. And via holography, we map this of vacuum generators to that of Chern-Simons serial level and on T2. And so today I only focus on the ground state. Basically, we don't know much about the behavior of excited cell, or how can we understand? Maybe it would be better to first focus on the half PPSA. It will be much easier to analyze. And also various implications you can think of acting as duality and so on. So this is summarized for today's talk, and maybe I should make some concluding remark for our lecture series. So in this lecture series, I illustrated several holographic approaches to study quantum gravity, although they are all discussed separately, but they are in fact deeply related, and to study the quantum gravity spectrum on AdS in a very quantitative way. And this offers a concrete framework for reconstructing bulk in the supersymmetric sector, and maybe provide some lessons to finite temperature physics. So what makes these studies even more interesting is that there are still many important questions. So in the first talk, I constructed the QFT duals to non-regular black holes, but you can ask what will be the large N QFT duals for supersymmetric hairy black holes, or can we find some new settles dual to new geometries, genuinely new geometries with different horizon topologies? Can we have this different horizon topology in AdS space? And analyzing supercharged cohomologies, we probe the behavior of particle excitation outside the horizon, and which is ultimately related to the supersymmetric hairy black holes. And given that, one may ask, what can we learn about the interior of black holes from these supercharged cohomologies? Maybe giving some answer to the information problem and other important problem of black holes. And today I illustrated the ground state in the presence of orbital singularities in these AdS-CFT examples. And we know not much in these AdS-CFT dualities. So what will be the behavior of high energy states in this twisted string sector will be very interesting. And there are many other questions. So despite many things have been done, there are still many exciting areas to explore. And I hope my lecture series will give you some insights on this holographic quantum gravity, and, well, give a chance to our starting point for our wonderful cooperation. Thank you for this.
Thank you very much. So I think we have more questions. There were quite a few questions during the talk, so that's thanks Sunjin for your time.
Thank you.